Thank you. Oh, hello, it's nice to be here. My name is Srihari. I work at Nilenso. I see someone here wearing a Nilenso shirt. Great. I've been writing Clojure for the last 5 years, about. And at Nilenso, Nilenso is a cooperative. It's a hackers collective based in Bangalore, India. And so we've been working on large e-commerce, low latency, distributed systems in Clojure all this time, and I've had the experience of building test systems for substantially large systems, and I found a lot of commonalities in the way we've been writing generative tests. So that's what this talk is going to be about, the learnings from that. So I'm probably going to be taking all the 45 minutes of this, unfortunately, because I have a lot of material to cover. So, and I'm pretty sure that I'll be available for questions throughout the day. So let's do question answers there. Quickly, what I'm going to be doing in this talk is talking about why I'm talking about this, about this at all, and what it is. And I'll give you a practical system, an example based on which the entire talk can be understood, some benefits and problems of generative tests, and then I'll establish some terminology, a base set of understanding that we can take forward to understand the patterns. The patterns themselves are divided into 4 different other categories I'll get to when I get there. So quickly, why? Tests are good, right? We should be writing tests for our software. Generative tests are better, right? Like John Hughes made this case quite a while ago. Quick check has been replicated in 30 languages. I presume people here are familiar with test check and the like. It's not new to the Clojure ecosystem at all. But I have found, like in talking to people, that we don't write them often enough. Like I went around talking to people at the Conj. Most people say, yeah, I've written some generative tests, I've written some unit tests, some algorithms that I've like tested here and there, some data structures. But then when we dig in a little deeper, like do people really like write integration tests and system tests generatively, and why don't they do that? So that's a bit of why I'm giving this talk, because I'm hoping we can start thinking about those things a little better. And so what I'm going to be talking about is are all these things, which is automating software testing in general. Generative tests exist because, well, one of the reasons is that we are too lazy to write enough example tests. My case, the case I'm making is that maybe we're too lazy to write generative tests as well. So why not automate the whole thing, right? And so some patterns around how we can go about thinking about that, but more generally, this is not about the specific patterns themselves. This is a certain thought paradigm I'm hoping to sort of get across via patterns. So. What is a practical system that we can use to understand everything that follows? I think we can take a generic e-commerce system, something that we are all familiar with, right? Like imagine you have Amazon or something, and then you have a user can sign up or be created, they can authenticate or log in, you can update a cart, add things to your cart, and remove things from your cart, update things, quantities, etc. And then you can pay for things, you can get them refunded, you can apply offers, and then all that jazz. So a very simple path, happy path, can be that you sign up, log in, and then add a card, add a payment card, add something to your cart, update it, and pay, right? Seems fairly straightforward. We consider this system for the rest of the talk to understand how we can generatively test this. So the next part is about how we can maximize the benefits of generative testing. So we have to understand what the benefits are, and then minimize the problems so we understand what the problems are. The benefits are that, at least the hypothesis is that generative tests are better than humans at input generation. right? This is not the minus infinity, minus 1, 0, null, plus QA kind of inputs, but the entire range that the machine can give us. Of course, we'll be writing thousands of tests, running thousands of tests generatively rather than just a handful of example-based tests, so we hope to get more coverage. And just from a broader perspective, we're looking at finding or having a better chance at finding bugs before users do, right? The problems, though, are I've found primarily some inertia. Like people, I like my example bases. I want to write them, and so there's a bit of a learning curve as well. So I definitely recommend John Hughes's talk at Clojure West. I'm not going to be going into the benefits and how-tos of generative tests in this talk. So John Hughes' talk at Clojure West is great. And for learning curve, I think Gary Fredericks, the maintainer of TestCheck, does a really good job of taking you through how to write custom generators and such. So you can watch those. So one of the difficulties is in thinking in properties. So if you're thinking of circular buffers or sorting algorithms, it becomes very easy because it's academic. You can read it off a book. You can think of properties that you can write. But the moment you have CRUD APIs and creating a user and logging in, how do you generatively test that, or what properties does login have? That doesn't make any sense, right? So that's something that inhibits us from writing generative tests. The other thing is that it's slow. So your example-based tests run in 5 seconds. Generatively, you're running thousands of tests, it quickly goes to 5 minutes, and then you add more generative tests, and then it becomes 20, and then 40, and then that becomes really difficult because you need quick feedback loops from your CI. The other thing is that there's this notion about generative tests where they are relevant enough. Say, in this e-commerce system, you have things in your cart. The generator adds 1,000 items in your cart, and you're like, well, of course it's going to fail for 1,000 items. My system isn't built for that, and I don't really care about that, but it fails my build, right? So that's not a situation you want to be in. And the assumption that more tests means more coverage is not necessarily true, because you can write 1,000 tests and have it all hit the happy path and have it all pass. So there must be a way for the tests to be somehow domain aware so that they can do a better job at that. And they are also high maintenance. In all the systems that I've worked in, there's been a full-time software engineer, senior, on it full-time. And so that's kind of telling. Why that happens is because the tests are dependent on source, and as source moves, you have to keep maintaining your tests, right? And the other thing is that these things can be very difficult to diagnose. If you're running system-level generative tests or simulation tests, what ends up happening is it's basically like debugging your system in production, where you have thousands of users, lots of logs, trawling through multiple systems, trying to find out what exactly the issue is. And finding the root cause can be quite difficult with generative tests. So that's roughly the set of problems we want to address. And so to understand the thought paradigm I'm trying to get across, let me try to establish some base terminology. So I'm thinking of 3 different segments in tests. These are completely orthogonal. So a test can be at a particular phase, testing at a particular level, and have a particular focus. And roughly, here's what these things are. So phases is your very popular acronym of arrange, act, assume, arrange, act, assert, or assume, arrange, act, assert. But for generative tests, I believe that this is more well-suited. So there's generation, there's execution of your tests, and there's property-based assertions, and then there's diagnosis. Diagnosis is actually a phase that most of us leave out. Like, what do you do when something fails, when your test fails? What are the tools that you can use to diagnose your bug? And then there's a level. So there's the famous or infamous test pyramid, if you will. There's unit tests at the bottom, which is supposed to be cheap. And as you go up, you have higher level tests that are brittle or slow, but they have higher value. But with generative tests, I am questioning sort of the pyramid to some extent, because if your system tests can be as easy to write and provide, they do provide a lot of value, and if they become less brittle, why not write more of them? That's what you care about, right? Your end users, and if you can hit your system like your users would, why wouldn't you? But then if you take this thought to a bit of a fantastical extreme, why not write only system tests? Because if you have the ability to debug your a failure very easily at the level which you can with a unit test, with generative system tests, why wouldn't you just write system tests all the time? But of course, that's only fantastical. It's just something that I wanted to say. And there's of course focus. So each test can have one or more focuses, but I think with generative tests specifically, there's a tendency to conflate multiple focuses. So we can test for correctness. So these can be like build tests or smoke tests and acceptance tests. There are regression tests which you have to ensure backward compatibility. There's of course performance tests. Like load stress, endurance, etc. And I guess generative tests can be each of these things separately, but not necessarily more than one at a time. And here's an abstraction I want us to consider. There's a notion of a system under test, or SUT, but I'm going to call it an action. And what I'm doing is I'm going to consider a single function or a group of functions or an entire system as a single function. Right? Your entire system can be just a single function with an input and an output. Your input, if it's a single function, is like a function argument and a return value. And if you have like a HTTP level test or something, you have your request response. But there's also a notion of state. So all your third-party integrations, all your I/O, I've just modeled up into state. And state is also input and output because you're putting your system under a particular state before you test it, and you're going to test the state of your system after it's being tested. You're going to write assertions based on that. So state is also in the input and output. And a testing software is a software in its own right. So in that perspective, you're going to have to think of what are the things you're trying to automate. So these are the archetypes that we're trying to automate, I think, which is number one, ourselves. We write example-based tests and generative tests. We want to automate that. And we want to automate some of what a QA engineer does with all their domain understanding and notions of how to break the system. With that, we can delve into patterns. So let's define it. I am throwing any notion of a software pattern out the door for this talk. It comes with a lot of baggage, and for at least for this talk, I'm going to consider that anything that we've seen occur kind of again and again is something worthy of being noticed, and something that we should look at and say, hey, maybe there's something there, maybe it's leading to something else. And that's all I'm hoping to provide via patterns. The patterns themselves I'm going to take in 4 phases. Each of the phase, when I'm talking about each of the phase, I will try to look at different levels of testing, like unit integration, and try to talk about them. However, like most patterns, these thoughts and these patterns are not linear, right? Like I'm not going to talk about one thing and then gradually build up to the others, because these patterns are inherently intertwined. Although it's a linear graph here, what it is actually a cyclic, definitely non-linear graph somewhere. And so some of these patterns are forward referencing, some of these patterns are backward referencing, but I'll try to do my best in presenting it all in a cohesive manner. So we look at patterns in generating input. Don't bother to read the things on the right and go into them. So first thing I think we should consider is writing param specifications along with the functions. This helps in writing tests. Why? Because when you write a test, say a unit test for something, say you're doing a login, and then you change the specification of the email, or change the specification of the username, or something like that, you have to change it in your test again. Instead, use the parameter specification specified in the function. So I'm proposing something like def action, where we write a param schema. Right? And the param schema itself can just be your prismatic schema, Clojure spec, or whatever. But what you get out of it is the ability to generate inputs directly. So your test libraries give you these things for free, right? Like prismatic schema and Clojure spec. So this is great. And one implementation thing is that you have to write custom generators, and you learn how to do it. But for a huge system, you probably only have a handful of these. But what we want to get to is here, which is you have a single assertion that says, okay, there's no error with this action, and I just want to give the name of the action. In this case, it's user created, and it's a qualified symbol, the qualified keyword, rather. And that's it. I'm not going to specify the parameters. I'm not going to say how to do it, right? So this is how I want to test a single action. I just want to say, I don't want any errors in this action. And what do I mean by running this? It means generate the parameters and execute it. And exec action knows how to execute it, right? And this is for some notion of error, which can be a true the falsiness or something, or your HTTP request response or something. Right? So that's one. And then now if we have understood how to generate a test for a single action, what about multiple actions? What about the part where you say, in order for this action to run, I should have run a few things before this? That's the arranged part of your test, right? So if you have this way to declare an action, you can also declare its dependencies. And I propose we use tags or directed acyclic graphs to represent these dependencies. Quick examples. So user create has no dependencies, but to add an item into a cart, the user should have logged in, right? That's authenticate. Or in the case of payment, in order to make a payment, the user should have added a card, right, so that you can make the payment, and something should be present in the cart. Right? So these two actions should have occurred before this, and notice that these dependencies are transitive, right? So payment pay requires add card, which requires something else, which requires something else. Now I have declared everything that needs to be run before. So now I have a way to run assert no error for all the actions. So I have 10 to 15 actions. I can just make a list of them and then say there should be no errors in my system, no matter what, like no exceptions. Right? And this is great because you've already gotten there just by saying how to run a single action, test for a single action, and then for a simple thing like no errors. So what about the part where you actually execute the test? That is, what next, right? Like you write, okay, do a login and then use those parameters and then make the next call. That part of it, right? I propose you use probability matrices to define flows. And I guess what a flow is just a sequence of actions, right? But more importantly, these flows describe your users' behaviors. Right? For example, what I mean in this probability matrix is after running a user create, there's a 90% chance, there's a 90% chance that you run user authenticate, which is logging. Right? So the 10 other times, or 10% of the times, the user just fools around clicking on other things. And after adding an item to a cart, there is 30% chance that another item is added, etc. But you can use this to model user behaviors. And as examples, think of infrequent users, right? You want to model them and say, okay, infrequent users add things to the cart and then go away. And then after the session expires or whatever, they come back and add another thing to the cart. You can emulate that using probability matrices. Say you have 50% of your users are rich people. Rich people never ask for a refund, right? So I can say, the probability of payment pay to refund is 0. And that's a nice thing, right? You can also say that my app will never have somebody who does anything apart from login after doing a sign up. Like I just won't allow it. And then you can make that probability 100. What I'm getting to is the fact that you can model behaviors and make your tests more relevant. So you won't spend all of the time, so say you spend an hour running generative tests in CI, those, whatever time you spend is useful because you're testing flows that you care about, not just anything random. So with this, an example of the sequence of actions that you'd get would be something like this. So like user create, authenticate, add, update a few items, apply offer, and then cancel the payment. Another thing that maybe we wouldn't write an example-based test for would be something like authenticate, add an item, and then apply an offer, and then add items after that. That's not something that you would consider a normal flow. So these things exist, and it's important to realize that it's not just the action name. We already know how to generate the parameters for these actions. So what a flow is essentially a list of actions with parameters that say, this is how you make a request. And in the spirit of making your test more relevant, what you can do is use some deterministic seed data. So say in the case of 50% of your rich users, you already create a user, log them in, and add a card with sufficient money, say, right? And then you generatively test the rest of your flow. So what you get from there is, you know for sure that there's no error until the part where they add a card. And so you only care about all the failures that happen after that. So when you look at your test results, you know exactly the kind of data that you're dealing with. You've already set it, yeah, right? And so your deterministic seed data can emulate your end user. And for most enterprise organizations with like 4 or 5 kinds of users, this is quite nice. Another thing that you'll chance upon when you think about software systems as complete software is that they don't model entities that they should. So as an e-commerce system, we wouldn't model the amount of money in a user's card because that's not relevant to the system. But from a testing point of view, we probably should, because we're trying to be the user, right? And then if you want to capture half the people who have enough money to pay and then don't, you can do that. Another thing that you can do is, say, model the inventory of a supplier, if you're thinking about that, where it's like, okay, this person orders something, but the supplier doesn't have enough of it. So you need to model the supplier, although your system has nothing to do with the notion of a supplier. So that's it for generation, I guess, unless there's a backward reference somewhere. So there's execution, I'll delve into it. But before that, again, back to this abstraction of an action. There's an input, there's an output, and now we have talked about how there are ways to decide what actions come before and what actions come after. So there's actually a life cycle, which is that after you run an action, you decide whether you want to run another action or not after this, right? And so that's that part. And then you need to figure out what are the parameters you're going to use to make the next action. And then it's a cycle. But I'm going to ask you to make a leap from there and listen to me when I say this is a pattern that you need to store everything in your tests, or this is really useful. And I mean store literally everything, your inputs, your outputs, your generated params, the params you actually use, everything that you can store it. And before we get into why or how that's useful, let me tell you about how that's implemented really quickly. I use DataScript. Did I say immutably? I meant immutably. Store everything immutably. So I use DataScript. I store the request, response, and state in this example, and every action has the metadata of an action ID and a flow ID, right? And what this lets you do is do something like this. Like at any point during the test, if I want to see what are the items in a user's cart, I can just write a simple query. This is data log. If you're not able to follow along, I'll just explain it for you, which is, given this flow ID, give me all the SKUs in the cart. Since I have stored all the requests and the responses, I can do this. Similarly, if I want to find out what are the params for a given action in the past, like I've already made an action, what params did I use for it, I can go query it, right? Given this flow ID, give me the request for this action. And another thing, interestingly, that you can do if you store everything is get the timeline of a user's actions through your system. So if you have large systems and microservices and such, you have this tracking ID thing that you use so that you can track what happened in service 1, service 2, service 3 for a single user, right? And often the diagnosis is difficult because you have to go look at logs of 3 different things, and so you have some way to write down everything linearly. Your test is making all the requests, so if you store everything there, you can build a timeline easily and you can diagnose it, right? So that's, again, another benefit of storing everything. So there's actually a bit of magic that I don't know if you caught in the earlier life cycle about how you figure out the parameters for the next request, right? just because you create a user with a username of Srihari doesn't mean that you log in with a username Srihari, because that's also generated. So one thing needs to feed into another, and that can't magically happen. You have to do something to automate it. So what is that? And this is what I found. Just use the latest one. So if you store the request of the username, the response of the username, and any other call that you've made with a username, just pick the latest one. In all of them, and you can do a very simple query to figure that out, and that's mostly the thing that's relevant. So what you can do is, like this is the query, right? Like, find me this attribute name and sort by the timestamp and give me the first. So that's what this thing is, which is that you have the generated params. You take the generated params and then get parameters from your state that are relevant, mush them in, and then push them off. But before that, there is a notion of a param function, which is essentially a hook, right? So if you're writing some, like a lot of automation, one way to customize it or leave a notion for the user to customize it is leave a hook so that the user can change it. So here's an example. If I want to generate all the users with a prefixed username of gen user, I can do that. It doesn't need to be any random value. And like say when I make any payment, I need to choose a card from the user's requests before, right? It can't be just any card, so I can do that in the params function as well. And then the notion of hooks is more generic. It's not necessarily just to do with this whole parameter selection, but basically if you're automating a lot of things, you're going to have to want to customize a lot of things as well, because even if you have incredibly good sensible defaults, you're going to still want to customize, and hooks are great for that. Another thing you will want to do is, or rather I found myself doing, is cataloging errors. By that, what I mean is, if you're running generative tests for logging in, or say adding an item to a cart, there are things that'll fail, that will fail. Like if you try to create a user with the same username twice, it fails. You don't want half of the time that you spend going into these error cases, right? So if you note down the fact that there's a duplicate user, that might be a known error to this, or with payments, the session is inactive, or you have already made the payment and you're trying to make it again. These are known exceptions. You can say, okay, don't care about these conditions, move on from here, and then like test somewhere else where I think you would be more valuable. But of course, you can't just take it for granted that, if this is a known error you ignore, you have to validate that it is indeed an error condition. You can do this because you've stored everything, right? So at the time when you receive an exception, you can make a call to your system and say, okay, is this really true? So in duplicate user, you can find out, okay, does this user actually exist? In the case of payment, where you say that I've already paid for this and this is a duplicate payment, you can actually verify from your DB that I've actually made a request to pay and I'm doing it again. So another thing that is super useful when executing is if you can abstract out your request engine. It's not straightforward, but the notion is this, right? So you make API calls and you have API tests, and then you have controller tests. But they are mostly the same thing except for some serialization, some parsing, etc. So considering that your tests are literally the same and the inputs are actually the same, what only changes is the interface. So if you can abstract that out, what you can do is something like this, where you say, I'm testing in functions, or I'm testing at the controller level, take the same test and execute it at the controller level. So if it failed for something at the HTTP level and you want to narrow down your bugs, you can say, okay, get rid of all of the cases in which this can fail at the HTTP level. I only care about this from here, and then you can diagnose the failure from there on. And then we talk about assertions. So I've categorized patterns and assertions to 3 types. So there's algebraic properties, there's state machines, and there's domain-based invariance. Domain-based invariance is mostly here for completeness, because that's the thing that's kind of difficult for us to think about. So in algebraic properties, I made a nice table. There's no error, which is of course not really algebraic, it's also there for completeness. But you can look at egality, which is effective equality. There's idempotence, which is like run the same thing again, should be the same thing. There's identity inverse, and commutativity and associativity. I'll delve into a few of these, but the notion is to actually squint a bit at these because it's not directly applicable. Our systems are not algebraic, they are stateful and all that, lots of logic in between. But I'm hoping that these examples will give you an idea of what you can do to think about it like that. So no error is fairly straightforward, right? You have all your responses, you just take them through a function that says, okay, no errors, and that's something we've already talked about. But the usefulness of that is that you can ensure that there are no errors. So this, like for distributed systems, if you want to ensure that there are no timeouts or your systems are always up and available, this is a great test to have it. You can run it on every single thing. There's egality, which is effective equality. So say if you have a sign up, which creates a user and returns the user back to you, and you have user get, which is, it returns the user. So both these API calls give you the same result in the end, right? So to some meaning of equality, they are equal. They don't leave the system in the same state, but you can assert that these two things are equal. Similarly, an update that does a soft delete, it says update but change deleted to true, or like remove the item from the cart. They don't literally, in this case, they actually literally do the same thing, but you get what I mean, right? Like squint a little bit at your system and say that these two things are just about equal. Let me write a test for this that says so. And then there's idempotence, which is super critical if you're looking at payment systems or distributed systems, right? You don't want things to fail, and if you do, you want to be able to retry them, and the retries shouldn't fail for whatever reason. And so there are two classes of testing idempotent things. Say, I logged in, and then I log in again. People do this, right? Like something happens in your interface, and then you log in again, and you want to ensure that that works. So you keep your login idempotent. But what if you log in and then add a few things to your cart, go all the way to payment, and then log in again there? What happens then? So, like, since your system is in a different state, things might be broken, so you want to test against that as well. So there's immediate and distant, and so the right bottom kind of tries to describe that, where you have, where you say that this percentage of my flow should be filled with idempotent actions, and since you've already stored everything, you know how to make an idempotent call. You have the same parameters that you just made. And then you specify how many of your calls you want to be immediate and distant. And in my case, I have a blacklist of calls that are not idempotent, so I don't test for them. In your case, you can have a whitelist if your systems are otherwise designed. So that's that. And then there's inverse, which is if you add an item and remove an item, the effective cart get should be the same if you do a cart get before or a cart get after. So there's also normalized inverse. Some people call this round trip also, by the way. So there's normalized inverse, which is that a pay and cancel doesn't leave the thing in the same way, the system in the same place, but pay, cancel, pay is the same as pay. Right. And there's commutativity, which is that you add skew1, then skew2, or then skew2 and skew1, they're both the same thing. But you can add a little bit of sugar to this and say assert commutative and let the system make all the permutations of orders of the calls and ensure that it's commutative. And there's also value in asserting that things are not commutative. For example, updating the item as quantity to 1 and then 6, or 6 and 1. These things are not the same, so you can assert the opposite. So that's about algebraic properties. And another thing that's very common in most systems is state machines. So here, take an example of the cart that we had, the state machine of the cart. So the cart can be new, it can have items, and then it can go to a success if it's paid, or it can go to cancelled. And these are more or less all the API calls we have in our system. So what we can do is take this state machine and code it down. So what I have here is a simple code logic matcher, where I say that given this state and this API call, and if it succeeds, this should be the new state it goes into. So basically, this is a list of all the valid state transitions. Now that I have a list of valid state transitions, and I have all the state transitions that the system has been through, I can validate if there's been any invalid state transition. I've left out that that plumbing code, but you get the idea, right? You validate that your system has only been through valid state transitions, and this is incredibly useful. Then of course for completeness, there's domain-based invariance where you say something like, depending on your system and your understanding of it, you can say things like, okay, I created a user, or I created 10 users and I call the user list thing, and then they should both be the same. Or like you have a lookup active, lookup by name, lookup by ID, they should all be the same thing. You can say that the number of items I've sold in all these tests should be the same as the number of items that people bought in the end. You know, if you have two different API calls and things like that, you can assert those. And then there's diagnosis. Let's dig into that. We've seen action specs before this, right? And the example on the right. That is data. That's just Eden. And that is the input to your test engine. And as long as your system stays the same, this test input is basically your test. Right? So what you can do is store it and run it again another time. If it passes, right? Say you have your thing passing in V41, your version 41, your tests pass, and you've stored that test, and that test can now be a regression test against V42. The other thing with generative tests and a lot of tests is that if they run on CI and fail, you don't know how to debug them because it's been a very peculiar case that you can't reproduce locally. But if you have saved it, you can take that one error, put it on S3 or something, and then get it on your machine and run it, and it will fail. It's basically thinking of your test as data that you can take out to make your test deterministic and reproducible. A lot of times when you have, so the system, one of the systems I worked on had like about 100 different API calls, and it was difficult for us to find out where something was going wrong. So if you can think of your code as a tribe data structure, where each node has more relevant components of it inside it, then if you can narrow it down, top down, right? It gives you a more narrower scope to deal with. So for example, I can say that if someone added an item to a cart, then of course they have logged in, right? So let me look at the scope of errors beyond this. And it really makes a lot of sense to have domain, this kind of a domain injected into your test. So you need checkpoints that you enter yourself. And then you have flow timelines, which I kind of talked about earlier, which is that you can take a single user and figure out what happened throughout. But in a case of a failing test, what you can do is you have a table, because why not? Tables are great. You can have, say for example, all these things happened, all these different actions happened at different times, and the update item failed, right? There was an exception with that. What I can say is diagnose this action ID, and I've stored it, right? And with this action ID, I can say, okay, this is the metadata with it. This is the action spec. This is the request. This is the response. So you know exactly what happened, right? You can take a flow timeline, one thing that failed, dig in, one by one, and then you know what happened. So I think it's incredibly useful to have these kind of timelines and tools to debug your failures after your tests have run. And of course, there's a notion of automated bug reports. So your system knows when it fails, and you have nice tables, so why not directly put it on GitHub, right? So this is an example of the system that I actually wrote and the bug I actually filed, which is that you have a summary and you know what went wrong, and here's a stack trace. And this is another example of the kind of bugs. So there was a no error thing that we ran on the entire system, and that brought up 50 bugs on the same day. And it was like, why not just file it? And we made one ticket with all 50 items. And that's basically it. So to summarize, there's generative patterns, generation patterns, where you specify how to run a given action, how to run the actions before that, after that, how to model behaviors of users, how to make tests more relevant by giving seed data and modeling external domain. We've looked at execution, where we store everything and look at the value of storing everything, and then cataloging known errors and abstracting your request engine and how that helps. And in assertions, we looked at algebraic properties in state machines and how diagnosis really helps, like having really good tools in diagnosis helps. In effect, though, what I'm trying to get across are not the literal patterns themselves, but about the notion of automating software testing. I think software testing has come a long way since we started doing it with just plain manual tests. And I think generative tests are great, and I think we can do better. And these patterns are an example of how. And what I'm trying to sort of get across is maybe a thought paradigm more than anything. It's not the patterns themselves. As references, there's Microsoft PECS patterns. It's really well documented. They have this thing called parameterized unit tests, and PECS is a framework for that. A lot of the algebraic properties in there and all are quite well documented there. I used a simulant in one of my earlier projects, and a lot of these things kind of follow of that. It's a framework for doing simulation testing, and it's written by the Datomic team. That's quite nice as well. That's all I have. Thank you.
Okay. Thank you.
Do we have time for questions?
Of course, we have 3 minutes for questions.
Not bad. Hi.
Hey, I'm just curious if you thought about doing minification of the...
Oh, shrinking.
Sure.
Right. I think I had in one of my slides somewhere that shrinking is useful, but shrinking is not domain aware, right? So we have written some custom shrinking mechanisms sometimes, so you'll have to do that. But to be fair, I haven't done much of that. I find that like doing these things itself gives me a lot of confidence that things aren't failing, and the first occurrence of failure alone is sufficient. Like I don't need to shrink that to the minimal use case, because if I have the right tools to diagnose it, one failure case is sufficient for me.
I saw some other hands.
Yeah, there are a few hands here.
I was wondering if you had a sense of the size of your test code and data compared to the application itself.
So one of the systems was a payment system. It had about 30 odd modules of like interacting with external vendors, doing payments, doing analytics, etc., etc. So that's, I don't know in terms of lines of code or something. I can't think of it, but that was a lot. So I don't know if I touched upon this, but basically all those 100 odd API calls, if they are cataloged, like we had an action catalog, which then became the Swagger documentation of that. If you're deriving all of your tests based off of that, that makes it really, really small. And you're just writing the test engine then, you're not writing much domain code. If there is any domain-specific code, that kind of goes into the specification and the domains. And I had like a handful of specification namespaces and a couple of assertion namespaces and a bunch of code to write the test engine itself. I don't know if that answers your question, but that's roughly it. I have a kind of, this has emerged into a bit of a framework, so to speak, in the context of the client that I was working with. And maybe if I pull it out into a public repository, that could be something that you can look at to glean size difference or whatever. But yeah, you don't really write a whole lot of code.
I was wondering, how far do you find it to train developers to this kind of thinking? Because it's a lot of concepts and it's pretty generic. So.
I don't know the answer. I don't have an answer to that question. A lot of these things have just come up sort of organically. Like, just write a lot of tests, and then like you see patterns that come across, and then you just work on those patterns, learn forward. I had one other developer working with me on these things. He gave a talk at Clojure some time ago. He's learned fairly quickly. I think, so what we do is pair program. I think if you pair program and writing one of these test engines, it's not all that difficult. The concepts actually aren't that hard. I don't think so, at least.
So question about a multi-service case,
Yeah.
when you say model the external domain, does that mean what other services can upstream, downstream, or are you actually doing these tests on multiple running services, like a end-to-end style?
Could be both. So there's the notion of the user, right, of your system. If the user of your system is another machine, another system, then and you want to test your service independently from the other service, then you're going to have to emulate the other service to a certain extent within your tests. Right? So you have to model that. It becomes easy because you already know how to model that. You can look at the source code of that application to understand a little bit. But yeah, does that answer your question?
Any more questions? Okay, cool. Thanks a lot, Srihari.